So in this session, we are going to cover robustness of two population t-test. We are using Rice University's demonstration website. So let's start with the test on the right-hand side, two population t-test. The null hypothesis is that mu1 equals mu2, alternative they are not equal. And the assumptions, there are a couple assumptions here. Both the populations are normally distributed and the two population variances are equal. Then we have the test statistic t, and the decision rule is if the t value, absolute t, greater than the t critical value, then we reject the null hypothesis. Okay. So on the left hand side, we are going to do the demo. The top part here, that is the population 1, mean 0, standard deviation 1, and there is no skewness, so it's a normal distribution. The bottom one is population 2, the mean 0, standard deviation 1. Again, there's no skewness, it's a normal distribution. So from population 1, we are taking a sample of size 5. Population 2, we are taking a sample of also size 5. And the planned alpha is 0.05, so the probability of type 1 error, 0.05. And what we are going to do is simulate this sampling process 2,000 times. Then we are going to compute the true type 1 error rate. Out of 2,000 simulations, how many times we are rejecting the null hypothesis. We are counting that. So let me simulate once. I'm taking 2,000 samples. So out of 2,000 samples, 98 times I'm rejecting the null hypothesis. So the type 1 error rate is 0.049. So this is a true type 1 error rate, 0.049. Planned is 0.05, so the two are very close to each other. So when all the assumptions are true, in this case both assumptions are true, then your planned alpha level and then the true alpha level are going to be very, very close. So now let's say that one of the assumptions is not true. For example, the variance of the second distribution is 5, first one is 1, so significantly different. So in this case, if I simulate it, you see the type 1 error rate is higher, 0.076. If I keep simulating 2,000 more times, 2,000 more times, 2,000 more times, consistently you see that the true type 1 error is higher than the planned alpha level. Okay, so this approximation, t approximation, is not that good when one of the assumptions is not true. So now let me go back to the same thing, and I'm going to change the skewness. So let's say this is skewed and the second distribution also skewed. Now let me simulate this. So that assumption 1 is not true, and I'm simulating it. Now you see the type 1 error rate 0.038. Then simulate one more time, one more time, one more time. So that's different. Okay, so it's not exactly equal to the plan, but it's different. Now let me change that the variance is also different. So let me do that. So both assumptions are not true. Both are not normal anymore, and the variances are not equal anymore. Now if I simulate that, you see the type 1 error rate is actually 10%. So if I simulate one more time, one more time, one more time, you consistently see that the type 1 error rate is 10%. So in real life, we are not going to be simulating 2,000 times. We are going to take one sample from population 1, one sample from population 2, and with 0.05 we are going to make a decision. So we are going to be thinking that our type 1 error rate is 0.05, but the true type 1 error rate is actually 10%. So the true error rate is going to be different than our planned alpha if the assumptions are not true. Okay, so now let's say that I'm going to increase my sample size in both cases, and then let me simulate that. Now you see that my type 1 error rate is 0.06. So simulate one more time, one more time, one more time. So even though both assumptions are violated here, but if I increase my sample size, then the true type 1 error rate is going to be closer to the planned significance level of 0.05. Okay, so in summary, if the assumptions are not true, then the true type on error rate is not going to be exactly equal to our planned value of alpha. Thank you.